Hi guys, welcome to the world of physics infinity. In this particular video lecture, we are going to have a very interesting situation of three concentric spheres. Radii R1, R2, R3, hollow metal spheres. I can have numerous problems based upon this situation, but I will take one very typical one, that these three plates X, Y and Z are of radii, hollow metal spheres of radii R1, R2, R3. Between the plate X and Z, a cell is connected of EMF V, and the middle plate Y is earthed. Five important things I am asking in this particular situation. First and the foremost, what are the charges on the different faces of these plates? X1, X2, Y1, Y2, Z1, Z2. 1. Once we do the charge distribution, then we can work out the PD between, let's say I'm asking you the PD between X and Z. Of course, Vy would be 0. 2. Number 3, to find the capacitance of this arrangement. Number 4, the field pattern, the electric field pattern. And number 5, the potential energy stored by the system within the field associated with the system. So this is, now if you can follow this, then I can have so many other problems based upon this. I can earth the first one, I can earth the last one, I can connect, well, I can take that one as another problem, but let's take this typical problem first, one by one. So let's say, if the PD, if the EMF cell is connected between X and Z, then suppose the charge Q is supplied. Now here I'll have to find Q also in terms of R1, R2, R3. So it's going to be quite complicated later on. But let us assume the cell pushes charge Q. So Q is given to the plate X and minus Q is given to the plate Z. Of course, the plate Y is earth and both the faces of Y, Y1 as well as Y2 are bound faces. Why? Because in front of Y1 there is X2 which is charged, and in front of Y1 there is X2 which is charged, and in front of Y2 there is Z which is also a charged body. Let's see now. On X1 charge is 0. Of course, no charge will reside inside as usual. Then on X2, all the charge Q pushed by the cell comes on X2, where Q is equal to CV. Once I find C, then I can tell you exactly how much is going to be Q, because V has been given to us. On Y1, it will be minus Q, Gauss's law, and on Y2, let it be Q dash. Let it be Q dash. It's a bound phase. So let it be Q dash. Of course, Q dash will be a fraction of Q. We'll see later. On Z1, it will be minus Q dash by Gauss's law. And on Z2 is Z is a floating plate, so the total charge has to be minus Q, so it will be minus Q plus Q dash. So our first problem is, what is Q dash in terms of Q? What is Q dash in terms of Q? I have one condition, and what is that condition? Plate Y is earth. That means Vy is 0. I use the superposition principle, and that is Vy equal to 0, potential of Y due to X due to Z, contribution 0. So let's see. So this gives me Vy equal to 0, it's an earth plate. So KQ by R2 due to X1 minus KQ by R2 due to Y1 plus KQ dash by R2 due to Y2, face Y2, and due to the entire Z, I don't have to split it up, minus KQ by R3 equal to 0, where K is the field constant 1 by 4 pi epsilon naught. Solve this, I get Q dash as a fraction of Q, that is R2 by R3. Once we know the charge on the various charges on the various faces, we can easily find the potential on each face, on each plate. Anyway, Vy is 0, it's an earth plate. And then we can find Vx minus Vz. Once we do that, then we can find capacitance, but one by one. Let's find Vx minus Vz. So Vx is equal to kq by R1 due to the plate X minus kq by R2 due to Y1 minus plus kq dash upon R2, but q dash is q into R2 by R3. I just put that value, that is contribution of Y2, and the contribution of Z, total Z charge is minus q, so minus kq by R3 contribution of Z. Easy, that gives me Vx equal to kq by R1 minus kq by R2. Let's go on to Z, the plate Z. So kq by R3 due to the plate X minus kq by R3 due to the face Y1, kq dash upon R3 due to Y2. I replace q dash as q into R2 by R3, and then the contribution of Z itself minus kq by R3. These two things cancel, and I get Vz equal to kq R2 by R3 square minus kq by R3, that is kq into R2 by R3 square minus 1 by R3. Fine. I get Vx minus Vz, that is the PD between X and Z. kq common, 1 by R1 minus 1 by R2 minus R2 by R3 square plus 1 by R3. I crack k 1 by 4 pi epsilon naught. So q upon 4 pi epsilon naught R2 R3 square minus R1 R3 square minus R1 R2 square plus R1 R2 R3. Now once we know PD, Vx minus Vz in terms of Q, now we can easily find the capacitance of the system. X and Z are cell points because the cell is connected across X and Z. X plate gets Q and the Z plate gets minus Q, which is pushed by the cell. So here you are. So C will be Q upon delta V. That will be Q upon Vx minus Vz. We already know Vx minus Vz in terms of Q. We already done that. So I just put the value. I put the value of delta V, that is Vx minus Vz. So C is equal to Q divided by Q upon 4 pi epsilon naught. I am of course cracking K. 1 by R1 minus 1 by R2 minus R2 by R3 square plus 1 by R3. That gives me 4 pi epsilon naught divided by R2 R3 square minus R1 R3 square, that's simple maths, minus R1 R2 square plus R1 R2 R3, and the LCM was R1 R2 R3 square. This goes up, this remains down. So C is equal to 4 pi epsilon naught R1 R2 R3 square divided by R2 R3 square minus R1 R3 square minus R1 R2 square plus R1 R2. But now that we know the capacitance, we know the PD, we can now work out the potential energy linked up, associated with the system, within the field associated with the system. So let's see here. Electrical PE, very simple, is going to be half C into V square. V is the EMF of the cell. So half, I just take the value of C that we have just calculated, evaluated. So 4 pi epsilon naught R1 R2 R3 square V square divided by R2 R3 square minus R1 R3 square minus R1 R2 square plus R1 R2 R3. I just put the values. This 4 cancels with 2. So 2 pi epsilon naught R1 R2 R3 square V square divided by R2 R3 square minus R1 R3 square minus R1 R2 square plus R1 R2 R3. You can try that also with the energy density method, which I have taught in my earlier video. Okay, just an exercise and see whether you get it by integration and energy density and the limits. We know about the charge distribution on the different phases, so easily we can work out the electric field pattern. To understand the electric field pattern, let us go to the original diagram. Let's see here. X1, between center to X1, there is no field. I don't show any line. Phase X2 has Q and this has minus Q. This is Q dash and over here is minus Q dash and over here is minus Q plus Q dash. Fine. Q dash is fraction of Q, but it is plus. Both these are minus. So how will be the field? Think of it. The field is radial, no doubt. So from infinity, it comes over here, infinity to Z2. No field within the conducting materials. Then from plus Q to minus Q, it goes. So from X2 to Y1, X2 to Y1, radially outward. So this is radially outward. Then from Y2 to Z1, Y2 has a positive charge, this has negative. So this is the field pattern. Now within this field, of course, energy is stored. You can do that. If you want to do it by integration, by energy density, you will get the same answer. Try it as a good exercise. So this brings us to the close of this particular situation that we have discussed in the case of three concentric spheres. I have already told you, in the case of three concentric spheres, we can have a number of problems. I may take on some in some other videos, but this is all that we have discussed regarding where the middle plate was Earth and a cell was connected between X and Z. I hope you have liked the video. I hope you have understood. I certainly, first of all, thank you for listening to me, one, and number two, of course, if you like it, put a thumbs up and also subscribe my channel so that you keep on getting my videos. Thank you.
If you love the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.